So, welcome everyone. Today's NPA speaker is Rithya, who's an assistant professor of physics at Vanderbilt University. Her research focuses on experimental QCD and jet physics. She's a member of the S-Phoenix experiment at RIC, also the CMS experiment at the LHC. And she's also involved in the physics program of the upcoming electron-ion collider. And today we are going to hear about energy correlators. So
and Jetscape.
And Jetscape, of course. So please.
All right. Well, it is super fun to be back to my old haunts. Really nice to see a lot of friendly faces, some new faces, super nice. So plan for today is really going to be this measurement and the sort of aftermath of this measurement, right? This is the measurement of the 2-point energy correlator in proton-proton collisions and lead-lead collisions. This is the first published measurements in lead-lead for the energy correlators. What did we do to get here? Why we did this? More importantly, when we look at this figure, what are we learning, right? What are the different feature spaces? And what are the next steps? What have we done to go past it? So I know, just to start with a pretty broad introduction, energy endpoint correlators are essentially a technique that we kind of, it's okay, come, that we kind of adopted from the cosmological groups where they studied it. They studied the correlation structures of the cosmic microwave background, right? Where you want to see what are some local inhomogeneities, what are some local structures compared to global structures, right? So once you look at the cosmic microwave background, you have all these different modes, and each of the modes tell you about something interesting in the microscopic structure, right? Essentially, we do the same thing in the case of particle collisions, where you have these collisions, you have these quarks and gluons that come out of these collisions, they evolve in space and time, and at some point they convert into hadrons, and then they hit your detector. So what we are truly measuring is essentially this collection of hadrons that are kind of way in the aftermath of the collision, because these things happen for like a Fermi over speed of light, which is 10 to the minus 22 seconds. And what we measure is something much later, okay? So this is the equation. Don't worry about it. It's not that much detail. Essentially, you're taking the correlation of two energies of particles at a particular angle that you want to study. You normalize it by some quantity that makes it comparable to each other, right? A more experimental friendly definition is you take the energy or the transverse momentum of particles, multiply them together. This is specifically for 2-point correlator. If you want to increase to 3-point and 4-point, you just EI, EJ, EK, L, M. You kind of extend the out, right? So that was a funny moment. Yeah, and then you plot it as a function of delta R, which is the distance in the pseudo-rapidity azimuth space in our detector, or you plot it as a function of angle, or some quantity that measures sort of a distance that you want to study this correlation space, right? And we can do this within a jet or within an event, and I'll talk about both of these, but let's go through a more operational version of this. What does it look like, right? So you run your collision, you get these particles that come out. Think of the green ones are the ones that belong to your signal event. You guys are late. Welcome. Yeah, you are very early. That's good. You're 5 minutes early, which is perfect time. So you have this definition of your jet that comes out from these collisions that have a bunch of particles. They also are a collimated spray of particles that result from your high energy quark or gluon. So imagine a very high energy unstable particle going this way, it's going to radiate, right? And we know radiation happens at very low energies, but once you boost it, the radiation, like the angle of the radiation gets Lorentz contracted, and so you get this conical structure of particles. That's essentially what we call a jet. Now, I put two different colors because they could also be background that are uncorrelated, but on a particle by particle level, it is near impossible to say whether one belongs to the signal or one belongs to the background. So we end up doing this kind of ensemble-based subtraction, which I'll talk about in a little bit. So step one is to always reconstruct your jets based on whatever you want, do whatever definition you want, and you decide on a particular axis in the middle, whether could be the jet momentum axis or the winner-take-all axis, which is just sort of the highest energy particle in your jet. Define that as an axis. All you need is some definition that tells you where you're going to draw your middle line, right? Once you do that, you draw a circle around it, you collect all the particles within it, you make pairs, and then you start to make your distribution. So let's say we start looking at pairs. Let's say we do these two, right? We fill in the distribution at that particular value of delta R, and we fill in, a histogram is a counting element. It essentially counts how many times something is happening. Instead of putting in a weight of 1, when we count it, we actually include the product of the energies. And you can also divide by some general scale if you want. I'm just making it relatively simple here. Just multiply the two particles' momentas and you get the height, right? Now, these guys are very close to the middle of the jet, so they are relatively higher momentum. The length of the arrows kind of correspond to the momentum, right? So when you take a pair that is kind of further away, you're left with a slightly smaller product. So you can kind of see how you build this distribution up, right? You go through all of these pairs of particles, and let's talk about what are the necessary feature spaces where we have interesting physics, right? If you make this histogram, the large angle region, large angle in relative terms, we're not talking about very large, but it's still in the region where sometimes we call it delta R, capital R sub L. They're all the same thing. Doesn't matter. We will not fix on a word, on a label, we will keep doing it, whatever we want, right? Sometimes it's also called XL in some CMS publication. If you want to come up with a new thing, feel free to do it. You guys are measuring things. We need more chaos in the world, right? So at large angle, what does this shape look like, right? It has a negative slope. It's kind of falling down. And what this is, you can directly extract this shape from perturbative QCD, right? If I have a quark that's radiating a gluon, that radiation essentially is a function of the energy of the gluon and the opening angle of the emission, right? And we know QCD in general follows like angular ordering. So as you go to wider and wider angles, that's kind of early time in terms of the emissions. And then you start out with a wide angle and then you get to narrow angles, right? So you can extract this feature in the large angle region to be sensitive to QCD. And therefore, you can use it as an extraction of alpha S. So this is one of the first publications that used this particular approach to extract alpha S. This is from CMS. And this has now 81 citations as of yesterday. And you can actually see this came out in 2024. And you see here two different bits, right? Here's the XL. Essentially the same thing. It's just the 2-point correlated, the distance between any two particles, right? The y-axis is just the 2-point correlator, normalized to however they want to do it. The black points are the data. Each of these different colors are a different Monte Carlo with certain bells and whistles kind of varied, right? So it's not really relevant what is in each of these. What is important to know is that some of them have interesting differences when you compare to data. So this already tells you that the model is sensitive to something, right? This observable is sensitive to some changes in the model that you're picking out, right? And what you can do is take a ratio of 3-point correlators to 2-point correlators at different jet momentum regions, right? For low momentum jets at CMS compared to very high momentum jets, you take a ratio of these correlators. Now, think of this very, very simply, right? If I have an extra radiation in my QCD phase space, right, I will need to include another term of like alpha S in my simple Feynman diagram, right? So essentially this ratio ends up having sensitivities to the value of alpha S that you put in this particular case, right? Feel free to stop me if there's any questions. So they did this ratio, they fit it, and this is also being done here with the Alice collaboration and the Star collaboration. So this is really a field where people are trying to put a lot of work in and trying to extract how this alpha S changes for different jet energies. And this is really, really small. And then you go to even ridiculously small energies at BRIC, where you get 10 GeV, 15 GeV jets, which if you multiply by the jet radius, the scale, the effective scale you're talking about is 2 GeV or so. So we're really, really close to lambda QCD as opposed to what we saw here, right? So we can plot the slope of this ratio as a function of jet momentum. Okay, technically it's 103 citations as of yesterday. I changed this slide, but it did not change the slide before. That was as of November 8th, okay? Because that's when I gave this talk before. So we can see that this slope changes, and you can calculate what is the corresponding value of alpha S that has this particular slope. And that gives you an experimentally extracted value, right? And there's some theoretical uncertainties based on the modeling that goes into this. And this is the first and the most precise measurement of alpha S using jet substructure, whatever particles are inside the jets. We have much more precise values of alpha S looking at just ratios of jet spectra, but this is sort of the first step in this process. Okay, so we're not done there. So what did we do? We can look at these 2-point correlators that have where the energy exponent is 1, where you're just multiplying the two energies and asking it as a function of the angle. So this is the same measurement I showed you, same style of measurement that you see here on the left. And we are now doing this at a slightly different jet energy with a different data set in CMS. We compare to different models, and they more or less do a reasonable job, right? They're off by roughly 20% or so, 15, 20%, like probably at the most, if you say, maybe even just 10%, right? Once you increase this energy exponent to higher values, you start including higher order effects. Was that a question?
Kind of, yeah.
Yeah.
Because on the one before, on that one, it was very different. What's the difference there?
What's what?
Because you were like, oh, there's actually pretty big differences between the model and the data. The left there.
Oh, this one?
Yeah.
This is zoomed in. This is 10%.
Okay, so it's not that. Okay.
Yeah, this is 10%, and then
okay.
we zoomed out here. So
Okay.
if you see 10%
Yeah.
here, this is the same kind of problematic effects.
Got it.
Right?
Yes.
And once you go to higher order exponents, it gets much worse, right? So again, this is further evidence that this observable has sensitivity to these factors in, and this making measurements like these really helped our theory colleagues to then improve their calculations to include all these higher order effects, right? And we're also looking at 1.5, 1.5, 1, and 2. So you can essentially try and scale out what is the dependence of these exponents, and that helps in the case of improving theory calculations. So I talked about this large angle region, right? We already know that it is sensitive to perturbative QCD, right? So what are some effects? If I have quarks versus gluons, immediately we know that the color charge of gluons is different. The way gluons radiate are fundamentally different than how quarks radiate. So if I compare the different flavors, this is work done by my postdoc Zhang and a graduate student Nuno, and it's now published. You can take a look at the reference there. What we compared is just the shape of the 2-point energy correlators for quark jets in the red markers and gluon jets in the blue markers, right? So immediately, what you see is there is a difference in the distributions, not just the overall scale of the distributions, the shape of the distribution is also different. And interestingly, what you notice is that this difference is not only in the perturbative region, right? When I change quark initiated versus gluon initiated, we end up kind of changing things everywhere. And it's kind of shown in this figure here, which is the black markers are we collect a subsample of jets that have 50% quarks and 50% gluons, just like an average sample, right? If I increase my quark fraction by 10%, I get the green marker here, right? If I increase my gluon fraction by 10%, I get the purple marker. So what does that do to my ratio? It completely changes the distribution up to 10%. Why is this relevant? We are going to talk about jet quenching. We are going to talk about jets going through the plasma, right? And we think of quark jets kind of having less energy loss than gluon jets because gluons have a larger color factor. When they move through the quark-gluon plasma, they interact more, and therefore they lose more energy. And therefore, your surviving quark and gluon fraction might be different in your population. So if you see a modification in the data, it doesn't mean that the jet quenching effects modified this region technically. It could be that this is a subset of all the different modifications that happen in here, right? So that's what I'm trying to say. There are different regions have different sensitivities. Okay, everyone following me? This is a little bit tricky. I just want to make sure everyone's good.
This is in Pythia. Have there been similar studies in like Herwig's?
Yeah.
Okay.
We compared different models. This is like Pythia 8. We looked at different photon showers that have different shower algorithms. We looked at, this is Joule with this Pythia 6, which has a different way of like ordering the shower. We also compared to Herwig, but we didn't put it in there.
But you see kind of the same.
Yeah.
Okay.
Mm-hmm. We also looked at quenching cases. Once we do the energy loss, what happens? And that's also in this paper. That is actually the next slide. Good. So we also looked at the ratio of these 2-point energy correlators for quark jets divided by gluon jets, right? And what do we see here? The filled markers are vacuum, so that's proton-proton. The open markers are medium, which includes like energy loss effects, but then we made it kind of simple, so ignore that part. It's not the most realistic, but it does do like energy loss. So we really wanted to see, in ignoring this large angle region, which we know to be perturbative, if I make a perturbative difference in my sample of jets, is the difference still here? And the answer is clearly not, right? There are, throughout the entire regions of the phase space, you have sensitivities to perturbative effects. So I'm kind of stressing on this because we tend to give talks, and I'm guilty of it too, where we talk about this observable as neatly separating perturbative effects and non-perturbative effects. And that is not entirely true. It's true for most cases. It's not entirely true. And these are important effects to factor in when you're trying to extract physics from the data. Okay? So back to the data. This is what the data actually tells us, right? Here's the ratio of lead to PP. These n=1 correlators are the one where you just multiply the two energies together, and you see this massive enhancement at very large delta R. And when you increase the exponent to 2, it suppresses this large angle enhancement, but then you also see this small angle enhancement, which was sort of a surprise when we made this measurement. I think there's a reasonable expectation that you will see this, and I'll come to it later once we talk about what the peak actually represents in these distributions. And what is useful, at least to start with, is you can see these ratio markers, these ratio plots. It doesn't matter what is plotted here, right? We all know that the data is in the black. Each of these are different theory shapes, right? Different theory models, different calculations, right? None of them get the data really well. Some do better in some areas, some do worse in some areas. The thing that is really annoying is this blue marker. This should not work this well, right? This blue marker, Joule with recoils, is jet evolution with energy loss. It is not a fully accurate representation of the physics. It is a limiting case of what happens in the case of jet energy loss. It also doesn't have the full hydrodynamic evolution of the plasma. So it is a very, very simple perturbative QCD model that doesn't have anything other than just 1 to 2 energy loss, right? And it actually does reasonably well. So then you can ask the question, is this observable sensitive to different parts of the physics that we're talking about, right? If you look at this model, for example, they included the inclusion of wake, which is you imagine a boat going through water, you're going to pull part of the water with you, right? You have these wakes that are following you. If you include those wakes, do you actually get this enhancement? And this model tells us the wake is not enough, or maybe we need to do something a lot more. But anyway, it's not exactly clear what is the cause of the difference in the data, right? I had originally hoped for this observable immediately distinguishing all the different effects and telling us this is the reason what is happening. But, such is life. Things are not easy. We have to do more, right? One thing that we had to do, and this is something that I think we're all kind of familiar with and we're kind of expecting, in order to see this effect, we have to remove background, which is a very, very annoying process, right? It's even more annoying because if you look at the 2-point correlator, this is at CMS energies. The blue marker is your signal, right? It's falling down, this beautiful perturbative shape, like I talked about before. The black marker is what you would expect to see if you put your jet in a heavy ion background, right? The signal to background is really, really bad, right? So you have to extract anything you see here. I mean, what we see in this distribution is a 40% effect, 40 to 50% effect, right? We need to find changes between here and here, essentially. And we need to extract it from that much background that is there. So how do we do it? We use this kind of combinatorial background subtraction. It is a mixed pair selection. So what we do is we have our jet triggered event. We look at two different events that have exactly the same global event characteristics. We take the circle that we drew in our signal event. We draw exactly the same circle at exactly the same position in those different random events that do not have the physics that you're potentially looking for. And you can start making pairs. You make a pair from here, you combine with the pair from there. That gives you the signal fake background. And then you have to correct for the fake background. So we do this procedure. This equation gives you the background subtraction that you need to do. And this is also done in like other experiments with a slightly different approach where you look at different cones, right? What is new is we have generalized this for any order correlators. And this is what we are calling the parsnip method. Parsnip is my postdoc Ben's puppy, and parsnip stands for procedural algorithm for removing soft endpoint interactions in the quark-gluon plasma. It is super fun. This took longer to come up with than this, which was a couple of days of work. What we did is we want to know what are the number and coefficients of these terms that we need to include, right? This is a pure combinatorial study, right? If I want to calculate my signal distribution for endpoint correlators, I have to look at all combinations of, let's say I'm looking at 3 particles. I can have signal, 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 which is what I want. I can have signal, signal, fake, signal, fake, fake, and fake, fake, fake. I have to remove 3 different kinds of background, right? And that is essentially what we compare with here, where J is the signal contribution and M are the individual mixed events that you need to select, right? And the lambda essentially tells you how many number of mixed events you include. This is kind of a pain to generalize in a code because this depends on that, which depends on this, which depends on that. I haven't fully figured out how to, I should say, the people who are actually doing the work haven't fully figured out how to put it into a neat package. We have it, it's almost ready, and we want to include it. And we actually tested it by hand up to 6-point correlators. We derived this using kind of a generalized formula, and then we ended up trying to test this, and it's actually going pretty well. It worked out until 6 points, including all the coefficients that you can calculate. And this is work done by my postdoc Ben and our graduate student Laurenette. So once you remove the background, we should pause though. Yes.
The coefficients, sorry, these are
Yeah.
just like the numbers.
Yeah,
not
these are
like- don't have,
essentially-
like, any like
These are essentially
Additional like
these things
calibration.
in here,
Okay,
right?
right, okay, that's.
Whether you do plus, minus, and then when you do the,
Yeah.
when you do the
So
3
some-
point, you have to do twice and then 6 times.
Yes.
Yeah.
Okay, thanks.
So this essentially gives you all of those coefficients with the factorials of how many pairs that you're including, or how many n polygons you're essentially going to take. But wait, so this is an interesting question that we were thinking about with an incredible undergrad, Olivia, who worked with us last summer and is hopefully going to join us for grad school. Fingers crossed. Let's see where she decides to go. We're removing a lot of background, right? We're removing on order of factor of 10 more background than the signal. But the goal of our studies is to look at the quark-gluon plasma. What are the properties of the quark-gluon plasma? What are the space-time evolution structures of the plasma? Is there some interesting physics in there that this combinatorial background suppression is killing, right? Can we study this? And that's what Olivia did using the Jetscape framework, where we can really play with everything that we have access to. We can change the initial state, we can change the equation of state, we can change the hydrodynamic evolution, we can change everything related to a heavy ion collision and play with it. So on the left, I have gluon jets with a certain single energy. So this is not a realistic dijet event. We just have a hydrodynamic evolution of the plasma, and I shoot a gluon through it at a certain energy. In this case, it's an energy at 100 GeV. On the right, it's a quark jet at 100 GeV, right? What are the different markers? The different markers corresponds to different momentum bins for the particles that I'm considering in the 2-point correlations, right? If I look at the very low momentum particles, you can clearly see the impact of background. I mean, it's essentially all background, right? If you look at this distribution, the background pairs are essentially just going as this positive slope, which is truly the Jacobian of this observable, right? Once you increase the higher momentum particles inside your jet, you start recovering the jet shape that we talked about, right? This perturbative QCD falling down, negative slope. So you have physics here for jets. The question is, do you have physics here for soft particles? Can we do both at the same time, right? So in this particular case, we ran the simulations with the specific equation of state that comes from lattice calculations to fits to data. It's called the hot QCD equation of state. So how do we study this, right? My immediate question was, the quark-gluon plasma is a fluid, right? It's not a perfect fluid. I mean, it's damn near perfect, but it's almost, it has shear viscosity, it has entropy density, it has bulk viscosity. When you have shear viscosity, what does it mean? It means you have different planes that have different amounts of flow, right? So why not, let's look at 3 particle correlations divided by 2 particle correlations, right? We already know that this ratio is sensitive to alpha S. I already showed you that. People extracted alpha S from this ratio in the perturbative regime. And you can look at this for different track momentum bins for quark jets and gluon jets. And these red markers are kind of jumping around because systematics is not great. The statistics are not great. This plot also does not have statistical uncertainties, but it will be finalized it will be included in the final version. So can we look at these 3 particle correlators divided by 2 particle correlators and see if we change the equation of state, do we see any difference, right? And the surprising answer, maybe not entirely surprising, but kind of interesting for us, is there's a massive change, right? First of all, this is a realistic equation of state. This is not a realistic equation of state because we just put in the ideal guess. We put in PV equals nRT for the plasma, which is wrong, right? So basic question, is there a difference? And clearly, if you look at the soft particles, there's a pretty massive difference in the slopes, right? The statistics are kind of jumping around, but essentially you see the spread With the ideal gas, when you put a jet through, it is completely kind of nonsensical compared to what you see here, right? So the next question is, what if we put two semi-realistic equation of states? Do we find a difference? And by the time we got to this, Olivia went back to George Washington and had to do actual work as a student. So we are waiting to have a little bit more time to finish this project up. But I think this is very, very promising. And it's one of the first steps. I think we can actually push this further, because there's a quote that people like to say is, one person's garbage is another person's treasure, right? I think we have been doing jet physics and ignoring the garbage, and all the soft people, when they are measuring two particle correlations, for example, they're measuring flow, they literally remove the background, calling it non-flow. Everything for them that is non-flow is jets, which is my signal. So why not do both at the same time? Why not study how the high energy physics talks to the low energy physics? There is another thing that I wanted to put in the bottom here, just as a, self-contextualize, just to be aware. If we have done these ratios of multi-particle cumulants and correlations for a very long time in the case of heavy ion fluid. That is how we know that this has sensitivities to shear viscosity. This has sensitivity to bulk, like entropy density and all these properties, right? What we are doing is now looking at the energy correlators. We are essentially looking at the energy flow across these different dimensions, right? Am I just redoing the same thing with like a new label in front of it? And I don't know this entirely if I am redoing the same thing. It is likely that it is a possibility that because of these pretty narrow momentum bins, you're essentially factoring out the energy products and you're left with sort of an average n particle counting correlation, right? Maybe that is the case, but maybe the mean momentum is actually not that comparable between them, and you can look at it across spectrum. So a lot more work would really, like theory benefit, like motivation, how to go here. But I think, as Ian was saying yesterday in our chat, this is really a new area to kind of explore. Okay, so that was a lot. Does anyone have any questions? Everyone's following me?
Have you looked at have you looked at these, like if you take the jet back out?
No.
Yeah, I think that would be interesting.
Yes. If I look at it without the jet.
Because it's like, I guess I would think, what if the jet's just completely washed out in all the fluctuations?
Right. If I just move just move the circle away from the jet, or look at it pure no jet background.
Pure whatever this is, hot, whatever the
hot QCD equation of state.
Does for the non-jet stuff.
Yeah, that would be a good baseline to compare with the difference. Yeah. Yes.
You understand the behavior with the different PT ranges, that it's kind of similar for the lowest, for the hot QCD, it's similar for the lowest PT, and then it goes down and then back up for the, I don't understand the non-monotonic behavior. For the ideal gas, it is monotonic, but then for the hot QCD, it's, I don't know if it's actually just.
No, because we are taking ratios of normalized distributions.
Yeah.
So each of these distributions are normalized compared to this. So the high PT one with the jet, this is exactly the slope that we would expect from the jet measurements that has been done in the past. I don't think we have looked at it in this region. So I think this is just a funny consequence of normalized ratios, self-normalized distributions, and then taking ratios, you see it's slightly different. This is truly weird. Like the particle production is just insane. Like it's just truly weird. You get very different number of particles than the very different number of high PT particles than low PT particles. So this is just something, can we put in completely wrong information and we see different? So basic test was satisfied. Right?
On the left, going from 2 to 4 is what I would expect for just increasing jet momentum to like for the running of the coupling constant. The sort of like it going one way and then going back and going the other way, I think could be the jet starting to peak out above the background, and then once we're fully in like the jet regime, then it behaves as we're changing jet. Like so like the 0.3 and 1 to 2 are like mostly background, and then 2 starts to be jet.
I think
so it goes one way.
2 to 4 is most likely, I would say, because this is at the LHC energies, you still have a lot of 2 to 3 GeV underlying event.
Yeah.
I think after 3 GeV and 4 GeV, you start to not have any underlying event. So I would think that the jet to underlying event ratio in that bin is closer to 50-50 and is completely dwarfed out in all of the other lower momentum bins. Yeah, so that's why if you compare red to blue, that's like a pure comparison of pure signal and pure background.
Yeah.
Right? Without any background subtraction. So that's kind of the idea to like study this effect. So we also did this, I showed this with Joule because see, there's history here. I worked on Joule, right? I know kind of to an extent what it is doing. We included background subtraction to make it better back in 2016. But it should not be this good, right? It should break at some point. And we thought we can compare different track momentum bins, different energy exponents, and it's like doing a reasonable job at most of the cases. Okay, it's not doing a good job.
Made the perfect model.
Corina made the perfect model in 2008, and it never needs to be changed anymore.
Yeah,
Right.
we're done.
But yeah, they don't reproduce all, but this is the advantage, right? You can look at different track momentums in here. You can increase the energy exponent. Each of those tell you different fractions of signal and background in your observable, right? And we're doing this completely differentially in this case. So let's go to the truly small, like the very small angle region. Now, if I have a simple thermal bath of particles, right? Just random distribution of particles in a given phase space. And if I ask for what is the distance measure of any two particles, that scales as the circle that I draw in this case, right? So it's essentially a pure distribution that has nothing to do with any physics between the particles. So it's this, what we call the Jacobian of the observable, right? So this is what we get when you have a random particle distribution. And this is also the region that people call the free hadron region or the non-perturbative kind of region, right? And this has had a lot of work done, especially by folks here and in these collaborations. Like Alice looked at it for many different models that have different like hadronization effects. Andrew did this for comparing like sign minus unlike sign divided by the inclusive. And you really see this massive difference between the data and the model that you did not see before, right? So what is it good for? Let's start keeping a tally, right? That was the title of the talk, energy correlators, what are they good for? Clearly like alpha S at some value. Not clearly, but definitely impacted by parton flavor dependence. Show modifications in the quark-gluon plasma that are not immediately easy to say they come from one particular source. And then now they show interesting differences for hadronization. There's been a lot more work on this, and you can definitely talk to Andrew or come to his PhD defense in a month, and he will talk to this at length. Let's go to the middle region, right? This is another interesting region. I think of this, maybe you can correct me if I'm wrong, or is that it's just kind of mean value theorem. You have negative slope, you have positive slope, they have to join at some point. You have to get zero slope at some point in order to go from one to the other, right? So if small angle is a positive slope, the large angle has a negative slope from physics, from pure random distribution, they have to connect at some point, right? What is the physics of that point, right? And this was actually a big kind of interesting thing that happened over the last few years when every collaboration was doing this measurement. We found out that if you take this distance scale and scale it with the average jet momentum, which is truly a virtuality scale, in this case, all the distributions kind of line up roughly, similarly, possibly, maybe, potentially. Any more words you want to include, you can include, right? Maybe this is hinting at something universal that is happening. And we know one thing that is for sure universally happening for every jet that is produced, right? For a fact, every jet is produced as quarks and gluons, and we measure them as hadrons. So universally, hadronization is happening in those jets before you measure them, right? So the large angle region we know is perturbative QCD. We can describe individual quarks and gluons. So let's say this is sort of the early time in the collision when quarks and gluons come out, they start radiating. And this region, very small angle, much later in time, it's fully random distributions of particles, right? You can even describe it with a pure like random model A times RL. That's also what's done here in the star paper in the function. When you go to very small angles, what you're left with is just scales as R, right? So what is the interesting region? Is this where hadronization is happening? Is there some potential significance to how we can tell where and when, specifically time-wise, when does hadronization happen, right? I don't know if we truly have an answer for that. I will wait to see if there's more theory guidance, but I think we can tell there's something interesting going on here. That is another thing this energy correlator is good for, right? One more thing is we can actually look at this for different flavor of jets, right? The peak of the jets have something quite interesting where three of the authors are in this room for this paper. One is in Los Alamos. Yeah. So if you look at light jets, which are up-down strange, you compare it with charm jets and bottom jets, you essentially have this kind of hierarchy in the peak distributions, right? What is that? That's essentially telling you the impact of heavy flavored jets that have a dead cone, right? There's a difference in the virtuality of the jet because it has mass in it, right? If the peak is sensitive to the virtuality, once you introduce a mass scale, you will start to see differences, right? Because you're comparing them at the same jet momentum, but some have higher energy, therefore higher virtuality, right? We did this with a high school student, Hudson at Vanderbilt. I forgot his high school name, but he's part of this national high school program that the students come to Vanderbilt and they do research, and they are scary. It is incredible. Hudson was a very, very interesting kid. He learned everything super fast, and he started doing everything without me telling him to, and that kind of became scary. But okay, so what we did here is we tried to kind of recreate the same thing that we see there, but at proton-proton collisions 30 to 40 GeV, which you're going to be interested in at some point. What we did is we normalized to the small angle region because we know there's no physics of the different parton flavor. Typically quark-gluon, yeah, there's a difference, but if they're all quark, is there a difference? Probably not. So we normalized it here, and then you can actually see the difference in the peak positions, and we fitted the peaks with a very simple Gaussian distribution and extracted the peak position, right? And we expect the peak to essentially scale as this lambda QCD with some function of the mass of the jet in there, right? And this is a picture of Hudson actually giving a talk at DNP, blowing people's minds that high school students can give talks that are incredibly well practiced and rehearsed. Dennis over there stood up and essentially said, this is a better talk than some of our senior colleagues can give.
Did you really say that?
Oh yeah.
That's amazing.
And I was sitting there and I was crying because my baby is growing so fast in front of my eyes, right? And this is the figure that we kind of ended up with, and he called it the resurrection of the dead cone. And we plotted, yeah?
Yeah.
What?
I was trying to be clever. I was like, oh, I didn't realize it had died. I didn't get the actual joke that it's a dead go.
Yeah, it is. This is how you know you are in the midst of thesis writing, is when your brain stops to function for
Yeah.
everything else, right? So this is the peak of the energy correlated distribution plotted as a function of the jet momentum for different types of quarks that initiate the jets. We did this for proton-proton collisions. We also did this for electron-proton collisions at the EIC, and essentially made a difference that highlights the impact of multi-particle, multi-parton interactions, the sort of underlying event in proton-proton collisions, the different kinematics of the X and Q squared that result in the jets that are being produced. So Ben worked very closely with Hudson, and then we actually fit this with a functional form to extract the mass dependence. And we have a paper that Hudson submitted to the Regeneron Science Talent Competition. And one of the requirements of submitting a paper to Regeneron is you don't submit it anywhere else. So we have to wait until we know if Hudson wins this competition or not, and then we can submit the paper to PRC or PRD or whatever it is that we end up doing. So that's why potentially accessible at RIC, but a definite discovery potential at the EIC. I think we can really figure this out, the mass dependence, and get closer to the virtuality scales that we are really interested in at the EIC. So flavor dependence is number 6 if you're keeping count of what these energy correlators are good for. Another thing, okay, I still have a little bit of time. I promise you I'll finish with this, even though I have some slides. We can go over it later. So we compared lead-lead to PP, right? Red markers, lead-lead, black markers, PP. We compared it at the same jet momentum. What do we already know? We know that jets in lead-lead went through lost energy. So this is not really an apples to apples comparison. And we already see the peaks are different, right? If we know that the peak is sensitive to the average jet momentum, is there a way we can use this to truly do an apples to apples comparison, right? Now, historically, probably even now, we are still going to compare the same jet PT. This is not something revolutionary, but I think we should start heading towards a place where we can compare. This turned out to be extremely accidental, what we did. And we actually have a functional form for a cumulative distribution that you can correct with Jack, Carlotta, Yusi, and I. This is published, you can go take a look. We can essentially collect this as a function of the energy loss, and we really get back to having no effect of energy loss once you do this cumulative distribution. Now, I don't have the time to talk about it in too much detail, but let's actually play a game with this. And Yusi did this. When I asked him on a plane as we were flying to Japan, we had proton-proton collisions 140 to 160 already done, because the unfolding for the data we did in 20 GeV bins. And so we said, why don't we plot the proton-proton collisions at a slightly higher jet momentum? I mean, you can't make this up. They are exactly on top of each other. So what does this mean? This means that the lead-lead jets potentially started out as a 140 GeV jet and ended up as a 120 GeV jet. That's your delta PT, right? So if you compare this blue marker to the red marker, you can see that the impact of energy loss is actually larger, right? You have to shift the ratio higher because you completely normalized this region, right? By selecting the correct Q square to compare to. Not the Q square after energy loss, but potentially the Q square before energy loss, okay? So we're doing a bunch of things right now. We are starting out at different larger angles. We are increasing the exponents. going to the full events, there's some very interesting physics that we can study, and also going to 3-point correlators. I want to show one last thing, is that this is a new paper that we put on the archive in December with our postdocs at Vandy and with Jack and Carlota. Is, okay, there's something very interesting that you do, right? We have to choose a circle. In order to, I told you in the very beginning, you draw a circle and then you choose the pairs in that circle. Now we know that jets, the true jets, the particle jets that come out of the collision are not confined by the circle. That's something you do as a choice. You as an experimentalist draw it by hand, right? It doesn't mean that the jets are fully contained in there. So if you actually take a very large circle, r equals 0.8, and you start drawing smaller circles, you end up with finding a missing fraction of your pairs, because the simple fact that the anti-KT algorithm is not a perfect circle, and you're not going to find all the pairs within that circle, right? You can also find additional pairs that are between, this is what we were talking about this morning, between 0.4 and 0.8, for example, right? So when, like, Alice measures 0.2, for example, they are measuring this numerator distribution. So the individual spectra between the Alice measurement and the CMS measurement, we should not compare them on top of each other, because they're not exactly apples to apples in the spectrum, right? What we found is the paper title is called Living on the Edge of the Jet. It's pretty fun. And we actually see this when you do energy loss with two different models, you get roughly similar effects, right? This one is proton-proton collisions, and you get up to 15% differences. When you do energy loss, it's actually slightly larger depending on what what model you're studying and what different jet momentum bins. And we figured out that we can actually factor this out as a function of the difference between the jet axis and the winner-take-all axis. And this beautifully comes out of the theory. And when you take ratios, this ratio doesn't really matter anymore, this effect, right? So why is this relevant, right? Let's say you have a theoretical model, right? You have a parameter for energy loss. If you're making a calculation of the energy correlator spectra, the individual shape, if you fit that to our data, and you fit the ratio in your model to our data, this energy loss parameter you get different results. So what is the correct value? The correct value is what you take from the ratio, which is what we are saying based on this, right? This is an exercise to say that we can actually extract this for increasing the precision of theory to data comparison in these measurements. I mean, this is a known concept. Ian will yell at me. This is a known concept in PP collisions. People do this for mass and so on and so forth, but this is kind of interesting to see. All right, I want to skip this thing, and we can talk about the full event correlator if you want, but where are we now? This is the pro and cons of life. You expect to see things you don't, but that makes it more interesting because many things to study, right? There's dominant effects of perturbative QCD and non-perturbative QCD. Regimes are split. Not entirely true. Universal scale, yeah, possibly, maybe. We need more theory input to tell us where we are. Background subtraction with the statistical ensemble works, but should you? Maybe. I mean, why not do both, right? That's always my, why choose, be fundamentally non-binary. And there are many different phenomenological explorations of these observables that tell us what are they actually good for. And I think we are learning a lot. So stay tuned. Thank you very much. I really enjoyed coming back here. Okay, questions? Yes.
Can you go back to slide 29? Obviously, great talk. So on Hudson's work, I was wondering about the difference between the light, flavor, and charm. Maybe you talked about it already and it went quickly, but
yeah.
They look identical to me.
No, there's a slight difference. The green is higher. This is a log scale.
I know.
So, but actually there's a relatively big difference in the peak that you can extract.
Okay.
The green falls out earlier and the red slightly goes higher.
Okay, my eyes
Yeah.
are bad, I guess.
And that's just for this one PT bin. And you can see it here. They are relatively close.
I was trying to look at it here, but here it's C and B, right? Those two?
No, the blue is like inclusive.
Oh, sorry, I
Which is
miscolored.
mainly light.
Okay.
Yeah, we switched the colors.
Okay.
It's fine.
I have a question on a similar note, which is the like relative difference from light and charm to
Yeah.
then charm and beauty, bottom, whatever you're calling it.
Yes.
The difference in those differences, was that expected? Like the difference from light to charm is much bigger than the difference from.
Ah, yeah. Because the charm is
Because.
about a GeV.
Yeah,
And the cross-section fraction to get a charm is much smaller than what? It's not as high as getting a bottom, right? Bottom is like 700 times and charm's like 250 times at these energies. It changes when you go to higher energies, but yeah, roughly.
I could ask you a question on, so for slide 30,
Yeah.
just cause, well, I guess not this. Yeah, so I would ask you, for the light quark, that I see that lambda QCD sets the scale. For the heavy one, you think like just the mass of the hadron? Or,
Yeah.
So I guess do you just want to compare it to the massless one?
Yeah,
That's
That's why we put this to make it relatively simple, to compare one subset, to like one bucket with a partonic mass to another bucket with a different partonic mass. But yeah, we could include the hadron mass for the identified flavor, make it more experimentally robust, and that will make it, the comparison that you are talking about.
Is it sensitive to so like if you do like
A D versus a lambda, for example.
Exactly. You're thinking you got it right.
Well, because we just talked about it earlier today. I've been thinking about it.
Can you see like the splittings between the masses at all?
Yeah, so we didn't look at it with Hudson, but Hudson is actually Allison number 2, because like Allison was the first high school student I had, and with Allison, it was Allison, Lucas, and then Hudson, and now Francesca, who's going to show very cool stuff. So what Allison looked at was essentially comparing the 2-point energy correlators, like without like just particle correlation, not like energy, for charm jetty events that go into D's versus lambdas versus D plus, D minus, like D0. And we didn't end up finding a definitive statement because we thought we could use the width, maybe the width of the distributions to tell us something interesting. But we did find differences, but it was not quantified in a way that we could proceed. But that is the thing that we should do more. But yeah, that'll be useful to check further with Francesca when she comes. John, why are you not here?
Hey, Rithya. I apologize. Last minute, I couldn't make it in. And so first of all, I want to say maybe when you're back at Vanderbilt, we could have a Zoom meeting and talk a little. I'd like to talk with you. But yeah. I had a question about your slide 33. And slide 33, I was already thinking in the direction I'm going to say, but you started to bring up, comparing jets at the same energy or different energies. And already I was thinking, is there any advantage to doing something like event shape engineering where you would look at the jet that's going with the bulk or a jet that's going, perpendicular and looking at EECs to try and get, information on the background, on, on the parton energy loss or what have you by looking at those different directions.
Yeah, I totally agree. I think that is one extra dimensionality that I have not touched in this talk, is to look at the correlation between the event shape variables and the jet variables. I talked about it with the equation of state, but that is also slightly different. This is a connection between jet going through different geometrical shapes in the very beginning, and that is a very useful way to talk about path length dependence, for example. Right? So
Great.
I think this would be a useful quantity to discuss if there's more path length that ends up with a higher amount of energy loss, right? If you're
Right.
if you're able to quantify the difference in the peaks, I mean, we are able to quantify this because the uncertainties are relatively small and we can control it, and it's also a 20 GeV difference in the bins. Now, if I imagine that the path length difference is scales as L squared, and the difference in the path length is like a third of a Fermi or so, then you're going to compare essentially a couple, maybe 5 GeV difference in the energy loss in these specific bins. And I'm not entirely sure that we will have sensitivity to quantify it, but that sounds like a worthwhile study to take a look at.
Or even in the models, for example.
Yeah, for sure.
Yeah. Okay, thanks.
All right.
Over on this slide.
Yeah.
Yeah, I thought this was so surprising when Jack presented this at Quark Matter, the selection bias correction. But this is, to make sure I'm remembering right, this is only taking into account the PT selection.
Only taking into account the PT selection bias.
Dependence is not.
Like comparing these two.
Yeah, exactly.
It's literally comparing these two.
Yeah. Okay.
And it's enforcing that there's no other difference at large angle and small angle. The only shift is the peak,
Right.
but we know that these are peaky distributions.
Yeah.
When you shift them and take ratios, you get the wings.
Yeah.
Right. So we have to make sure that we're not sensitive to that difference. And there is a reason this is preliminary, and this did not make it onto the paper because not worth the fight at that moment. Later. Once I have tenure, I will with bigger gravitas. All right, any other questions? Everyone good? Makes sense? Happy?
Okay,
Awake?
let's read your